Hello everyone, welcome to Telops end of the year data recap extravaganza or cornucopia. We'll let people come in just for a few seconds. So while we are waiting for people, I will just mention that we're supposed to be even three field application engineers. One of them had to go on an urgent training on the other side of the ocean, and the other one just happened to be sick today, sadly. And so it's just going to be me by myself, and we'll try to have a little bit of fun going over all that data that is very interesting that we've been gathering over 2024. So we have quite a few people coming in. That's great. We always love to know a little bit more about the experience of our audience for our webinars. So I'll start a poll. I just want to know your overall experience with infrared imaging. So you should see something appear on your screen now. Just click on the option that best suits your experience. So here we go. So how would you rate your knowledge of infrared imaging technology? No direct experience, but interested, considered it. You've had direct experience, or you even consider yourself an expert. Here is what we have. That's great. We have a great mix of people in our audience. Just some that are fully considering themselves expert, so welcome. Other that have direct experience, no direct experience. So that's really great. This is supposed to be just a fun but interesting webinar about a bunch of different kind of data that we have gathered in 2024, either in-house at Telops or with clients, with collaborators in research and in the industry. So if you have any questions, please let me know by the end of this webinar. I will do our best to answer everything. And if you've registered, you will receive those answers at the end when we send. All right. So the data recap cornucopia, as I like to call it, we're just going to go over a little overview of Telops. Some of you don't have any direct contact with infrared imaging. If you're here just to learn a little bit more about Telops and infrared imaging, that's great. I'll just do a very quick overview of Telops and our product line, just to understand what we're working with here for the kind of data that we've been gathering. So you have a little bit of a better understanding of what kind of instrument and systems we're using for that series of data measurements that I'll be showing today. And so after that, I'll go over multiple new ones. It's just a little glimpse into what kind of data we've been gathering and the kind of data that our Telops camera users are taking over just all over the world. So we have some hyperspectral data at the very beginning, some interesting new measurements, especially a new algorithm that's really, really great for new gas detection results and reports. We have some experimental mechanics data, some ballistic research data, some great HD imaging and microscopy imaging, combustion research, and also some new data with the Radia series and HDR M700, some data that hasn't been shown yet to the public. So quickly, a little overview of Telops. So we started in 2000 in Quebec City. So this is where I am right now. We employ over 90 employees easily with different advanced degrees from PhD, master's, engineering. We really are proud to be world leaders in thermal imaging, and we have a strong focus on research and development here at Telops. We're now part of the Exosens group. So it's really an umbrella family of companies working in optoelectronics, trying to cover the whole electronic spectrum. Also recently, Telops acquired LR Tech. So LR Tech is really coming into Telops, and there's some really interesting systems that will become part of the Telops product line, especially in atmospheric sounding and still in the hyperspectral Fourier transform world. but just focus on a different kind of application, a different way to do those measurements. So for a product line, we have the hyperspectral cameras. This is Telops' really expertise. So we have some amazing systems, best in the world. Otherwise, we have the multispectral cameras, which is really an in-between between the hyperspectral cameras and broadband cameras, which can have 8 channels rotating. So we have 8 different spectral windows that are acquiring approximately at the same time. And they can go quite a bit faster than hyperspectral camera. Otherwise, we land in the broadband camera range. We have our new high dynamic range camera, which I'll show some data, is an incredible leap in technology for infrared imaging with extremely wide range of temperature within a single frame. We have our fast cameras. So Telops offers the fastest cameras in the world for high-speed imaging, so really great high-end cameras. We also have the entry-level Spark cameras transitioning towards Radia cameras that I'll be showcasing at the end of the webinar as well. So a little bit of a closer look at our hyperspectral systems. So we have our legacy system, so the bulkier, large systems are a bit older, but they're still extremely powerful systems that do very accurate measurements for hyperspectral imaging in mid-wave and long wave. We have HyperCam Airborne Mini and just a mini ground unit. These are the newer models. The Airborne having a stabilization platform that allows for great and stable measurements in an airborne platform. So that means we can have that instrument in a fixed-wing aircraft, a helicopter, and we even have a smaller unit, the Nano, that's an R&D project that's suitable for drone deployment. So these are newer models. I'll show some data that we've acquired with these two as well in the next few slides. So just a brief overview of the type of application that we touch here at Telops with our many different systems. So we'll be looking at more data covering a lot of these, but just quickly, we'll be talking about ballistics, combustion here, experimental mechanics, which is quite a growing market, gas detection, a very important market for hyperspectral imaging, mineral identification as well. We can do some great exploratory work with hyperspectral data. We've got some great campaigns coming up in 2025, so keep an eye out for this. IR signature, of course, for infrared imaging, and additive manufacturing, which is also a very interesting market. No data on this specifically for this webinar, but there's a lot of users that will be looking for high-speed, high-end thermal cameras for that kind of application. And otherwise, of course, NDT for inspections of materials of all kind. Here we have a great image of an electronic chip, big image with our cameras. Okay, so I'll go over some new hyperspectral data. This first one is not particularly special, but it's a great example of how the hyperspectral data can be looked at when you do a measurement. What can you be looking for when you take a measurement? So if you're less familiar with hyperspectral data, this is a great example. So this is done at Telops. We have standard gases that we can release. This was a specific request at nitrous oxide, sometimes better known as laughing gas. So we had a release in front of a black body and outside as well for the customer. But we were trying to look at the signature of nitrous oxide and how well the hyperspectral system could detect that gas. Nitrous oxide has a great signature for long wave hyperspectral imaging, as we can see here. And when you look through a data cube with this kind of system, when you reach those peaks of the signature, either absorption in this case or emission, then you see a clear change in the image that can get brighter for emission or darker for absorption. So that was a great straightforward measurement to showcase the hyperspectral system, how well you can detect those gases. And we did those outside as well with different conditions, but I'll only be able to show what we did here with the black body. Another kind of measurement that we can do with our hyperspectral systems is on solid surfaces or solid films. So here there were people interested in plastic recycling research. And there's some really interesting measurements they can do with hyperspectral systems in that case. And polymers, plastics, typically the research is done on with visible near-infrared and SWIR cameras, so shortwave infrared cameras, because they're more commonly found in the community. But in the long wave section of infrared, there's some very interesting peak signatures that are sometimes easier to detect than in those other infrared range for those other systems. So they send some plastic films, the simple solid films, but that are thin enough to be transparent for the heat of a black body. So I set up some samples in front of a black body, and I was able to do some measurements for a multitude of different samples. I won't go into the details into who are doing that research or what specific kind of molecule or polymer they were looking for, but I can showcase an example of the kind of change we observed through the recycling process. So we had an LDPE plastic, the low density polyethylene, and there's an increase in molecule due to the recycling process. And we were able to see that change in the signature very clearly just by changing the samples in front of that black body. And you don't need a particularly high temperature for that source at the back. As long as you have a good thermal contrast and you see that absorption through the film, you can see a very clear change in the composition of the polymer through completely passive remote sensing in this case. So very interesting. On the other side, for gas detection, I mentioned the new algorithm. Our development team did an amazing job in putting together a newly improved DNI algorithm. And so you can see here with the original algorithm and standard processing that was done in the community for hyperspectral imaging, it's very difficult to not have false positives when you have a gas that can be close in signature compared to other gases. Like we can see, we have a list of gases that can be close to each other in the spectral region of long wave imaging. So those peaks can be close to each other. The algorithm can sometimes create those false positives, which is normal in that kind of advanced imaging processing. But with the new algorithm, we have a very discrete and singular detection of gases, even though when you're asking the algorithm to detect all those gases in the list, to look for all those gases, the new algorithm is able to just to identify that single gas, yes, that we know is acetone in this case, and not create any false positives. Not only that, but because it's able to discern that gas in a much better way with a lower threshold, we can see the gas through those different data cubes being present for a longer period of time. We have a much better understanding of the dynamic of your plume and a much clearer detection of your gas overall. So if you're interested in gas detection, please reach out if you're interested in getting that new algorithm, which is really, really, really impressive. So last thing on the hyperspectral imaging, a quick note on our methane service. So Telops does offer a methane service inspection service, yes, with our airborne system that I mentioned earlier. Nothing too special, but we've been really getting more and more demand and more data acquisition over 2024. And one thing that was interesting was the detection over snow. And that's something that's great with the long wave system. As long as you have that thermal contrast that I mentioned before between your gas and your background, you'll be able to do some great detection. So compared to other systems that can have a harder time when you're not on a perfectly level and just flat ground, which is a darker, warmer background, our long wave hyperspectral system is able to do a very clear methane detection even on snow covered grounds. So really nice detection a full testing measurement campaign that was done during winter with that snow-covered area. So let's move on to the infrared cameras directly, so not hyperspectral anymore. We've been doing some great experimental mechanics measurements. At the top here, this is a typical split Hopkinson bar. That kind of measurements is pretty standard in the industry. They're really the ones pushing the frame rate as much as possible with our cameras. This was done in Germany when I was visiting for some demos and conferences. We had a group at the Freiburg University doing some split Hopkinson bars in an amazingly long underground tunnel. And we're able to push that frame rate to 43,000 hertz to have a really clear measurement for multiple frames at the point of separation of that split Hopkinson bar. Sorry, so we can see that the playback speed here is extremely slow. This is kind of process that's almost instantaneous. So we really push the limit of our cameras as much as possible. And our cameras can go up to 100,000 hertz, but to have a certain amount of pixels in the region of interest and a good view of the scene, we're windowing not to the lower limit to really see the scene a bit better. Otherwise, at the bottom here, it's a really fascinating material behavior. So that's what happens with a magnesium alloy, in this case, the aluminum magnesium alloy. And we see very well what's called the PLC effect, or the Portevin-Le Chatelier effect. Sorry, there's an R missing. So it's a phenomenon that happens in a tensile stress test, where you have those dislocations happening in the alloy, but in a specific angle depending on the alloy itself. And in the stress test, if you're familiar with this kind of testing, you might be familiar with this PLC effect that does a peculiar effect in the stress strain curve that we have here. Now, not a lot of people have been looking at this with infrared, but those dislocations that are creating weird stress strain behavior are visible because they're creating a heat release at those specific angles because of the dislocation. And so we can actually see those dislocations and that really fascinating phenomenon appearing in front of your eyes with the infrared imaging cameras. So it's not a phenomenon that's as fast as the splitting or the compressing of the split Hopkinson bar, but it's a really interesting phenomenon, and people can actually understand the energy that's being released in that sort of beautiful phenomenon that we're observing here. Now, we have an interesting ballistic research group here. This was done in the US with my colleagues, Joe, which is supposed to be here today, and Ben Sauté, our product line manager. They went to that institute in New Mexico Tech. So in New Mexico, it's called New Mexico Tech. And they had the opportunity to look at a multitude of ballistics systems firing at different kind of calibers. As we can see on the left, pretty big calibers for some of them, like the one at the bottom. Apparently, they were insisting that this was not supposed to be called a cannon, but for those of us not in that field, it definitely looked like a pretty big cannon to us. But the images that came out of this were really great, beautiful images of muzzle flashes and explosions coming out of the ballistic research. And we could have a really great definition to understand the process of that gas expansion after the firing. It was quite a hot day, so our team had to try to cover the cameras. Of course, the cameras have a pretty wide range of operating temperatures, but when you're in the middle of the New Mexico desert with some sensitive camera and with sensitive electronics, you have to try to cover them a little bit to protect from the sun. This is a great example of super HD imaging. You can see the video here of a lake house in Geneva. Colleague Joseph Carrick took that. This camera has been doing the rounds, taking beautiful landscapes like we can see here, but also taking some interesting images for getting as much spatial information as possible when you're doing thermal imaging of a scene. So here on the right, we have a silicon wafer that will be somewhat transparent when using the midwave extended, so the midwave extended range of our camera. So that means you're pushing toward shortwave the range of your detector. And so that silicon wafer was able to be transparent, and you can detect those defects even better than before when using a super HD camera. You have an extremely high resolution compared to standard infrared cameras in the community at large. So this one was in Geneva, like I mentioned, in the northern part of the US. We have this camera did go to Korea, South Korea. So we had some great images that were taken there, and at a workshop in the US as well, some great super HD images that were taken of a mountain field. Now for microscopy imaging, some really interesting data that was taken in 2024. Some people were interested in a heating surface, but at a microscopic level. So these are very small grain, around 200, 300 microns maybe. So it's a very dark surface, so closer to a black body in terms of surface. But you can see there's non-uniformity in those grain. So with that microscopy lens, and we're talking about a G4X, so you're multiplying the pixel pitch by 4 to have your pixel resolution, spatial resolution. You were able to bring that surface to be from 20 to 600 degrees Celsius while maintaining that imaging. And by doing just simple processing here, you can see that non-uniformity of those grain emissivity. So all of these are at a same temperature, of course, but the surface microscopic differences and the material differences from some of those grains showed a pretty drastic change in temperature just due to change of emissivity properties. Otherwise, we also did some optic fiber detection, defect detection, sorry. So this whole fiber is only 1 millimeter thick, and we're able to look at non-uniformity stress that happened in the fiber or some defects. This group was looking at the option of doing even nanocrystal observations in infrared. So with that G4X microscope lenses, yes, we can see very well into the core of the fiber with a heated body. And in this case, it was a black body behind the fiber. And so you can really inspect the fiber and have the fiber roll in front of your camera at a relatively high speed to detect any kind of abnormality within your optic fiber. Another interesting measurement that was taken was on an actual housefly, so a common housefly, but looking at, so we had the eye measurement, but also the discal cells of, so that's the regions of those wings. So that's what's called those regions. And you can actually see the individual cells on that housefly wing using that microscope lenses. So really beautiful images that we're able to obtain over the year. Now, if we look more on the multispectral side of things, we have a really interesting data that was obtained in Spain, this one. So those people were looking at ceramic combustion research. So they are a ceramic facility, huge facility, factory to build ceramic, but they also have a research center looking at how to improve that process. And part of that process is the annealing process for the ceramic. And typically this is done with natural gas, but they're trying to get slightly greener, so have fewer greenhouse gas being emitted through that process. So they try to use hydrogen in this case. And with our cameras, with a multispectral camera that had an extended range, that midwave extended range that I mentioned before, allows for a slightly better visualization of water vibrational states. So with that extended range that we can see here, in our image, we can see the water quite a bit better than a standard midwave detector. So combining that with a multispectral camera, those 8 filters that we have here, we are able to see not only the water very well, but the complete absence of CO2 at that high temperature during the combustion process. So these were done exactly the same way at the same distance of the combustion. So the flame was simply gradually reduced from natural gas to hydrogen gas, to pure hydrogen gas. And theoretically, the hydrogen gas is really supposed to have water as its final product with that CO2, which is what we're observing here. So this was a great observation, a great confirmation of the process that would make the whole annealing process and ceramic production process a lot greener in this case. Something else that was interesting, more on the fluid dynamic side, and that was done with a standard 50mm lens, also a G1X microscope lens. We're looking at the water, not water, but fluid droplet splatter. So they're attempting to do mechanical and energetic analysis of that kind of phenomenon on different surfaces. So we had a sorry. So we had a metallic surface and we had a porous surface on the left. So we can see the behavior is quite different. And with the microscope lens, I would say it's really one of the worst case scenario when trying to do a tricky measurement. The depth of field is very, very difficult in that case. We're at an angle at a certain distance, and it's a fairly fast event. So you had to be really careful when you set up that kind of system. Your depth of field when you're at an angle with a microscope lens will be very narrow within your frame. So there's only one section that will really be in focus in that case. So you have to adjust it quite a bit. If it's possible to be really flat or perpendicular to the event with a microscope lens, that's typically the best thing to do. Now, I want to go over some data that was acquired with our new systems. If you looked at our webinar or looked at our website, you'll know that we've had the HDR M700 camera, which is, I would say, somewhat of a revolution in the technology for infrared detectors. That new architecture of the ROIC in the system makes it possible to have an amazing temperature range within your one frame. And so up to 900 degrees Celsius, or even much more than that when you bring up the calibration range. But when we're talking close to room temperature and above, we can have all the way up to 900 degrees, 1,000 degree temperature difference. Now, this was somewhat of a celebration event when the camera was finally released with some strawberry flambe. We can see the amazing contrast detail of the temperature range. So we had the picnic table here at room external temperature. We had those flames, and beyond the flames, all of this was none of this was saturated, and all of it was captured frame by frame with that amazing HDR M700. Now this is great and impressive on its own, but some people are already using standard cameras to have extremely high dynamic range by doing super framing or EHDRI, combining multiple frames and having each frame at a different exposure time. So it's possible to have those high dynamic ranges, but there's an issue when your scene is in movement. So we had a measurement set up here with different black bodies and a heater going extremely high. I'll slow it down a little bit here. We can see it a bit better. We had a fast moving scene with 2 black bodies and a heater going at more than 1,000 degrees Celsius. we had a black body at 400 degrees and the other black body at 1000 degrees. Sorry, 100 degrees, 400, and 1000. Yes. With the camera just by itself, every frame, you can see each temperature quite well. The contrast enhancement that was added to the Reveal software is always very useful. You can see the image super well, and the radiometric accuracy of that thermal data was maintained sorry, throughout that movement. So it had very good measurement. But now if we try to do that with a standard camera, and that's where it gets important to compare those, we have a pretty messed up image in this case. So this is, pushing the HDR to its limit. You get pretty absurd artifacts in this case when you combine 3 or more frames at different exposure times, where you can see the saturation in this case, or otherwise you have holes in your heater or a little higher temperature bits in the middle there. So artifacts that should not be there. Not only does it not look good, but the accuracy of the temperature gets completely messed up in this case. So it's completely off. The temperature sometimes can go even extremely high compared to what it really is. And when you compare it to the image of your HDR M700 in movement at quite high speed, we're talking 30 pixels moving horizontally per frame. We have a very, very clear image with the heater indicating its proper temperature at 1000 degrees Celsius. Now, another camera that's new this year is the Radia. So we have the Radia V60 and the Radia M100. These two cameras are really, the focus is the small swap form factor. So they're very, very small cameras. It's the first time we have an uncooled camera with the Radia V60 here at Telops. The M100 is cooled as well, but it's a much smaller system, much smaller cooler. We have, I would say, an exclusive image here with the M100. First time we're showcasing an image with the M100. We see that we have a really nice contrast in the image. We have the high temperature with the flame that's possible with the mid-wave range of the M100. And we have a very clear, sharp VGA, so 640 by 512 image for this one. The V60 is in the long wave, and it's even smaller than the M100. It has a lot of advantages to be integrated for multiple types of applications. And I'll show one great example is for automotive parts inspection. Typically, that's not a very high-speed moving scene, but you do need a high accuracy in your radiometric measurement. So those kind of tests were done on a car with which contains nowadays a multitude of heat generating systems. So we have the car seat heater, of course. We have the windshield defroster. We have the HVAC system that can go either cool or hot. And with the different lenses options, you can have a pretty far away shot or a very close shot where you can see actually the blades inside the HVAC system being heated up through the process. So a very small camera that is much easier to handle compared to our bigger high-end cameras, of course. Doesn't require a lot of power to generate, and it will have all the same functionalities as the high-end cameras within the software. So in terms of other kind of parts that can be inspected, you can look at, for example, we have that brake disc generating heat, of course, through friction, and you can have that hotspot detection mode where you can see where non-uniformities in your brake pad do generate more heat due to higher friction, of course. So that's an essential part of inspection for those kind of industrial research or industrial inspection lines. Brake pads being, of course, essential to inspect for the automotive industry. Otherwise, for electronics, so electronic boards, electronics in general, that are also applicable to cars, having a lot of electronics in them nowadays. The V60 is a really, really interesting one to use for electronic inspection. Once again, it's typically not extremely fast, but there are highly localized heat points within your electronic boards. So having that long wave range for that V60 camera offers a very sensitive temperature range and very accurate data, and that allows for a great inspection for all those mechanical or electronic parts. Finally, I want to mention medical imaging. We've had some really fascinating measurements, but it hasn't been a big market for infrared imaging so far. But I want to show these two images that were taken with an HD system. So we have the on the left, so great research done at the Sherbrooke University here in Quebec. So we have cancer clusters that were inputted in chicken embryos, and they're basically looking at how it evolves and how the metabolic rate of those cancer cells differ from the rest of the healthy cells in the tissue. And we can see with thermal imaging, there's a pretty drastic difference in that region of cancer cells. Similarly, not for cancer, but for vascular imaging, you can see those veins and those arteries having a clear difference in heat just through that HD imaging that we had here. So that was done with a mid-wave HD system. And you can see that you can get quite a bit of interesting diagnosis with this kind of imaging with infrared, and all of this being passive remote sensing. So it's very important to remember. So very quick to identify any kind of issue that might be happening in the patient, and afterwards you can dig a bit further with a better idea of the location of that issue. Now, I brought this after the Radia V60 data because HD images are, of course, very interesting for medical imaging, but the V60 has a slightly lower spatial resolution, but still quite a good VGA spatial resolution. And the extremely low swap form factor makes it extremely interesting and versatile to be integrated with other medical imaging systems. There's research being done, and there's some great measurement campaigns that we're looking into for 2025. So once again, keep an eye out for this. There's some great images, great data that should be coming out in 2025 for medical imaging. So if you're interested in this field, please let us know, and we'll probably have some very interesting data to share with you. So thank you very much for attending the webinar. This was just a quick overview of the kind of data that we've been gathering. Of course, we can't share all the data that we require with opportunities and clients, but these are the ones that were very interesting that we're able to share with you. So if you have any questions, please write in the little tab here, the Go to Webinar tab. We'll try to answer your question. I can see there's already some question coming in. Okay. So what's the price point of the M100 and V60? I can't really talk numbers during our webinar, but please contact our sales team here at telops.com. I will say that the M100 and V60 are obviously the low-end cameras, still very accurate radiometrically speaking, and offer a great versatility. And the price is much lower than the other high-end cameras that we'll talk about during this webinar. So it has a lot of advantages on that side. Yes, so when looking at the brake disc video, there was a hotspot in the corner of the brake disc. Is this real or a result of reflection? That's a very good question. Let's go back. There we go. Let's go back and take a look at this together. You were saying in the corner of the brake disc. In the corner, I don't know if you mean in the center or somewhere else that I don't see. But those hotspots are real, the ones that we see along the edge here at the center. If there's another hotspot that I'm not noticing, let me know. Yeah, so that's the red oversaturated bits. This is real results. So this is a mode in the software allowing us to really focus on those hot points. So yeah, this is real results, not just a reflection. It's just real results that we're able to detect that high temperature. Good point. Same video having low areas 6 degrees, which does seem low. Is this emissivity artifacts? There's a long story with emissivity correction in this video, but the 6 degrees is likely a true temperature, because this was in the middle of winter in February in a garage that wasn't perfectly sealed in terms of temperature. So we had a very cold environment. That brake disc, not the brake pad, was particularly cold, and the background was very, very cold. It being 6 degrees, it was in that range at minimum. So the emissivity correction when your background is colder than your actual object that you're looking at, your target, there's a bit of a twist that has to be considered. So you have to be careful and put all of those properties in your emissivity correction window when you do that change in Reveal IR. Yeah. All right. Well, if there are no other questions, well, I'll wish everyone a happy New Year and happy holidays. Those of you that do have vacations, hopefully you do. So have a great one. Thank you very much for attending the webinar. And if you have any questions, please contact us at Telops. So we have the email here, but the contact on the Exosens is working very well now. So if you have any questions, feel free to contact us through the website. Thank you very much.